140 gigahertz. That's way higher than what today's 5G frequencies. So, it's natural to wonder, is this actually dangerous? Does a higher frequency automatically mean higher risk? Or are we asking the wrong question here? Because when it comes to RF exposure, frequency alone doesn't tell the full story. Let's break down what really matters. From the previous videos, we already know a couple of important things. First, RF is non-ionizing. It doesn't have enough energy to break chemical bonds. And the second, exposure isn't just about the signal itself. It depends on power and distance. So, how strong is the signal? And how far away are you? But even with all that, we are still missing one key piece of the puzzle. Because there is another factor that really changes how RF interacts with the human body. And that's what we are going to explore next. First, let's clear up a very common misconception. When people hear 140 gigahertz, they immediately think that must be dangerous. But here is the key point. Even at 140 gigahertz, RF is still non-ionizing. What does that actually mean? It means this type of energy doesn't have enough power to break chemical bonds, and it doesn't directly damage your DNA. So the way it interacts with your body is completely different from things like medical imaging radiation. It's not the same as X-rays, and it's not the same as gamma rays. The risk mechanism here is fundamentally different. So instead of thinking about ionization, we need to look at a different effect entirely. And that's what really matters at these frequencies. Now, here is where things get really interesting. A lot of people assume something very simple. Higher frequency means more dangerous. It sounds logic, right? Higher number, higher energy. Must be worse. But in reality, that's not how it works. Because as frequency goes up, penetration actually goes down. In other words, higher frequency signals don't travel as deep into the human's body. They get absorbed much closer to the surface. So instead of spreading energy deep inside, the interaction becomes more shallow, more localized. And this completely changes how we think about exposure. It's not about the signal going deeper and deeper. It's actually the opposite. At very high frequencies like 140 gigahertz, most of the energy stays near the outer layers. So, the simple idea of higher frequency equals higher danger does not really hold up. Because what really matters is how the energy is absorbed, not just the frequency number itself. At around 140 gigahertz, the signal is absorbed within fractions of a millimeter. It doesn't reach internal organs, brain, or deeper tissues. It stays at the skin level. So, what does it actually do to the human body? If it's not breaking DNA, if it's not ionizing, then what's the real effect? The main answer is actually quite simple. It's heating. When RF energy is absorbed by your body, it gets converted into a tiny amount of heat, similar to how sunlight warms your skin. It's an energy transfer. But here is the part that often gets misunderstood. At the power levels used in communication systems, this heating effect is very small. We are talking about levels that are tightly controlled and designed to stay well within safety limits. So while heating is the primary mechanism, the actual temperature change is minimal. In most everyday scenarios, it's so small that your body can easily manage it. So the key takeaway is this. Yes, RF can cause heating, but at the typical communication power levels, the effect is extremely limited. Now, let's bring this into a real-world 6G scenario, because what actually happens in a live system is very different from what people often imagine. First, power levels are carefully controlled. Systems are designed to operate within strict safety limits. Second, beams are dynamic. They are constantly moving, adjusting, and tracking demand. They are not just locked onto one spot all the time. And third, signals are not continuously focused on a single person. Connections come and go, data bursts happen, and beams shift. So in reality, exposure isn't constant. It's intermittent and changing. And when you combine all of this, the actual exposure most people experience is usually much lower than they think. Not higher, not constant, but lower and highly variable. So the real-world picture is very different from the simplified assumptions people often make. And on top of all that, there is another important layer of protection: international safety guidelines. These are not random numbers. They are developed by expert organizations like the International Commission on Non-ionizing Radiation Protection and the Institute of Electrical and Electronics Engineers. Their job is to study the science, understand the biological effects, and define safety exposure limits for the public. And here is the key point. These limits already include large safety margins. We are not talking about cutting it close. In many cases, the allowed exposure level are set 10 to 50 times below where any harmful effects have been observed. So even before devices are deployed, they are designed to operate well within these conservative limits, which means in real-world use, there is a significant buffer built in for safety. It's not just about what's possible. It's about staying far below anything that could cause harm. To really put things into perspective, think about the energy you are exposed to every single day. For example, sunlight. It delivers much higher energy to your body than typical RF signals. Even the everyday devices around you, Wi-Fi, mobile phones, Bluetooth, all contribute to your normal RF exposure. And then here is the surprising part. Compared to all of that, the exposure from future 6G systems is expected to be much lower than most people imagine. So, while 6G might sound new and unfamiliar, the actual energy levels involved fit into a range we are already living with today. It's not something completely outside your daily experience. So, is 140 GHz actually safe? Let's answer that based on what we know, not assumptions, based on physics, based on our understanding of how RF interacts with the human body, and then based on established safety standards. The answer is yes. Under current exposure limits, 140 GHz is considered safe. And this isn't just a guess. It's backed by decades of research, careful measurements, and conservative guidelines designed to protect people. So when you hear 140 GHz, it might sound extreme, but when you look at the science behind it, it falls well within controlled and safety conditions. That's the key takeaway. But this is just the high-level answer. To really understand what's going on, we need to go a bit deeper. Because RF exposure isn't just one simple number. There are different ways to measure and interpret it. In the next videos, we are going to break it down step by step. We'll look at things like SAR versus power density, what they mean, and then when they matter. Near field versus far field, how distance changes everything. And then beamforming, how modern systems shape and then direct energy. Once you see all of this together, the full picture becomes much clearer. So if you want to understand this properly, stay with me for the next part. Higher frequency doesn't automatically mean higher danger. What really matters is something else. First, the type of energy. Not all electromagnetic waves behave the same way. Second, power. How much energy is actually being transmitted? And the third, exposure. How much of that energy actually reaches you? So, instead of focusing only on frequency, look at the full picture. Because safety is always about energy type, power, and an exposure working together. That's all for today. Thank you.